Hello everyone, my name is Evgeniya Hristova, I go by Jenny, and today we are going to dig a little bit in our project for advanced solidifiers for oil spill response. I'm representing Natural Resources Canada Research and Development Labs. We have 4 facilities. And I'm working out of the Devon, Alberta, which is just a small town outside of Edmonton. So this facility was built to support oil industry, and I've been working in bitumen oil and gas since 2005, so almost 20 years now. And since last year, with changing of the government regulations, we slowly moving to more sustainable and green energy. The project that I'm going to talk about today is a mature project for oil spill. This is the 6th year, and the work scope is almost complete. So now we are in Devon. We are doing a lot of bioenergy, carbon capture. My new project this year, we started to build hydrogen reactor, and we're looking for a safe way to store hydrogen as well. And you can see all other labs all over Canada. We have the material lab, and in Ottawa they also have bioenergy priorities. So this is all the different priorities that government set up. It's spread out throughout the country. Just quick overview of the oil spills. We call them accidental spills because apparently there's a lot of naturally occurring oil spills in the ocean, but we are talking about the major oil spills here in petroleum, and we all know that that's been a real problem for the ecosystem and the health and the environment. They have to be addressed as best as we can to our abilities. Just a quick overview of the oil response measure. Though on the left side you see the booming and skimming use of the adsorbents. That's we're going to talk about. Dredging, and sometimes we just have to leave it as it is, natural attenuation. So we were focusing our efforts on creating and developing a chemical that are naturally and safe for environment. So we are focusing on the spill treating agents like solidifiers and gelators. So this is just the overview of the different types of oil spill response. So what we're focusing is the sorbents and the low molecule weight gelators. Before we actually start developing all those chemicals, the first step is to really understand the aquatic behavior of petroleum products, because it's really important to understand after the oil spill where actually how the oil was distributed. And this project is applied to both river streams, lakes, and also ocean water. So it's really important to understand how salinity affects the distribution of oil. Also, as you know, in Canada, we do have a different type of oil. This is the heaviest existing oil that we call bitumen. So it's oil that is not mobile. It's really thick and hard to remove. So we're mixing it with light hydrocarbons. So if we have the oil spill, there's a lot of VOC in the atmosphere from the solvent. and becomes becomes really toxic. So we need to understand when the oil is spilled where it's going to go in terms of the water and in terms of the air. So this was the first step of the research in the first years. After we gained the understanding of the behavior, we moved to synthesizing the first product. So this is basically the one we took kind of a priority to go further with the investigation. It's not anything that it's totally new. This process is really well known for the industry. But we kind of have a little bit of tweaks to the system, so make it suitable for bitumen and conventional oil. And we synthesize it first in the lab, and then we scale up to a small pilot plant and then a big pilot plant. So we have the ability to actually synthesize quite a bit of solidifier if need to be. After the synthesis was over, what we wanted to understand is really the properties of the solidifier. And the most important property is the hydrophobicity, due to the fact that what we want to achieve is it's kind of a really fine powder, and if it's spray over the oil spill, the goal is to go and stick to the oil and nothing to be left in the water. Yeah, and it has really high hydrophobicity. So basically, we just finished this summer the pilot plant scale. It was interesting to watch when they spill the powder over a kind of a oil area. Everything that incidentally goes to the water spontaneously is attracted by the oil and get out of the water and stick to the oil, which was very nice to see and achieve. So of course the density and surface area is very important parameters, so we have to analyze it fully before we continue with other experiments. The goal of the putting chemicals basically can be really easily just come to the fact that all of those oil spills, it's a liquid with Newtonian behavior. So if you try to take it out or scoop it or do whatever, it's not, you're not gonna achieve anything. So basically what the chemical does, they bond deep with the oil and they change the Newtonian behavior to non-Newtonian and make it scoopable. And as you can see in those tables, CC stands for conventional crude and diluted bitumen. DB stands for diluted bitumen, which is our Canadian heavy oil. So the contact time to achieve solidification was very rapid, like 8 minutes to 32 minutes for the sorbent, and the percentage, however, for conventional crude was 50%, which was not like a good result. However, for the diluted bitumen was only 4%, which is a really small amount of chemical that needs to be distributed to achieve solidification. So after the, let's say 30 minutes, full 30 minutes, the oil is completely solidified and it's very easily scoopable and removable by any means, like any equipment that can be available. The gelator, which is not developed in our facility, but with people that we have joint research, also has a really good results similar to this, and it's just on the picture you can see The reverse, it just can sit in hours, and it's so dense and so scoopable that you cannot actually remove it from the bottom of the jar. And this is what we wanted to achieve by solidifying the oil. Before moving to our pilot plant testing, which actually our pilot plant test, you'll see a picture in the next slide, has ability to simulate the waves in the real time, in the real agitation forces. We try to do this in a small K in the lab. So basically, this is the apparatus, the rotary agitator you see is just turning and just simulating any type of turbulent flow that may happen in the river streams, or any type of waves even at the breaking point. So we use different speed to understand how the oil will interact when it's applied severe agitation. And this North Saskatchewan River water is our river, so which is for this one, we just use the water from the river. A very important part of our research is to understand how those solidifiers, actually the mechanism how they bond with the oil. And this is when I was brought up to this project because I'm managing all the microscopy in our research. So from the scanning electron, we have a really good scanning electron Hitachi microscope that goes to a resolution of 2 nanometers. And what you see here is basically the gelator going and creating a structure. It's almost like spaghetti looking structure, very long, like fibers. So this is this structure cannot be observed in any of the normal oils. So that's what the gelator and the sorbent does. They went. You can see the upper pictures are for diluted bitumen, and the lower pictures are for conventional crude. It went there and create those structures, and this is basically the process of solidification snapshot at nanoscale. On the other side is the just light microscopy with 200 times magnification. This is actually a water, a droplet that the waves took out of the pilot spill tank, and we just put it in the microscope and analyze it to see. So this is an idea what happened when the waves start beating the oil. It's basically they create a small, very, very fine emulsion, and they disperse it inside the oil, and that's why with the time this emulsion get more and more intense, and this oil droplet will become heavier, and eventually will sink to the bottom of the reservoir. And it's in again, we're trying to understand how the process of just going deep into the mechanisms and understanding how this is working. So this is from our spill tank. We do have a microbiology team that we are kind of collaborating inside our facility. So they were really nice to lend me 2 slides of their research. For the biological part of the study, it's really interesting. Okay, you spill the oil and you put those chemicals. What's going to happen with all the living organisms in the water? This was really important questions. And one difference between Canada and the United States, it's that here in the United States, it's allowed to use different agents or chemical to contain. In Canada, the legislation is strictly prohibited to use any type of chemicals to the water if oil is spilled. So for us, if we want to promote this to the government and be allowed to use those chemicals, we have to prove that it's safe for the bioorganisms and anything that is around this oil spill and may be affected by those chemicals. So the question we have to answer is, first of all, is the gelator biodegradable? And how all those bacteria will be affected. On the next slide, there's a little bit better understanding of this. So on this graph, the light blue is the most abundant bacteria that exist, proteobacteria, and what else we can observe that we have quite a bit of diversity in the water from bacteria. So we monitor and take samples from the pilot plant for 42 days, and the results on the other side basically is the results from this graph just fitted with this it's called after diversity in the species. So unfortunately those two chemicals did have a little bit effect and on the most on the diversity of those species. However, in real life, if you apply this to oil spill, because for 42 days we left the bitumen without scooping it from the tank. If this is used in the real life, the response has to be very rapid. So if it's 32 minutes to solidify, why we should wait and leave the oil there? It can be removed right away. So the next phase for us, and it's just this study is still in progress, is to understand what's the difference between leaving this product there or removing it from right away, and just understand if those bacteria community will sustain a little bit better. Also, every few hours we take sample and we test the water for different chemical and toxicity. And as I say, this is still ongoing investigation, but we'll have the final results by the end of March. So the other team that we are joined up do molecular dynamic simulation. So for the organogelator, we needed to understand how, similar to what I show you on the microscopy, we wanted to simulate the process. So the answer for those simulations is that there's strong hydrogen bonding. This is how the gelator and the sorbent goes and acts with the oil. And this publication is just accepted and published recently. So you can, if you're interested of more details on our molecular dynamic simulation, here is the link for it. And just an overview of our pilot. We have two spill tanks in the facility. They're in a temperature control and airflow environment. And we have a really good team of engineers taking care and operators taking care of this. So the schematic is above on the right side, but you can see actually here around the window, there's a lot of sampling ports. The level of the water goes just above the window, and it's 1,200 cubic liters. So a little bit over 1 ton. And we used, as I said, river water. The pedal that create the waves, it's on the left-hand side. And we have a pump that can generate a different agitation so we can have a really light waves, we can have a breaking point waves whenever we design to test this. And on this side is just the top, the picture from the top of the spill tanks when it's empty. And here is the pictures of our testing last summer. So we have a special device to spill the oil kind of a little bit evenly, and we calculate just by the desire of our thickness how thick we want to be the layer. In this case, we use 3 liters of diluted bitumen, and it takes quite a while to spread, maybe about 35-40 minutes. So then what we do, we start the waves, and you can see like it's probably not the best representation, but it's getting really messy. So by the end of the day, if we apply the solidifier as the last picture, basically, I shouldn't say by the end of the day because it's actually happened a little bit sooner, but in the first, let's say, in a working day, 6 to 8 hours, all the oil is at the end of the shore, and the water actually is cleaner, that kind of looking cleaner than it looked before. But we sample every few hours, and then we leave for all the tests. We leave the waves for 4 weeks, basically, and we sample for microbiology, microscopy, and that's how we understand what's going on. I didn't put the conclusions in the title because we have 2 months to go to finish this long, like this is the 6th year basically of the project, 5 years of laboratory testing and 1 year of pilot. So we investigated the behavioral spins, and our goal was to gain a better understanding and really optimize the response and the guidelines using our facilities. Then we were successful to synthesize a series of sorbents and show that these materials effectively contain spills of Canadian crude oil, diluted bitumen, on water. So at solidifier to oil ratio, the 4 weight percent is our best achievement. So in both laboratory scale and pilot scale, we investigate all the properties, including density, hydrophobicity, we show this, surface area, and also the most important is the performance of the solidification efficiency. And next one is the mechanism of solidifiers. We, as a research organization, we always try to go deeper to the problem and understand to nano level. We use microscopy, and we use molecular dynamics simulations. And the very key aspect, of course, of the study is the bio effect and impact of solidifier addition of all microbiological communities. At this point, we are just a month and a half away of completing the project. We're welcoming spill responders and all interested stakeholders to share the details of the knowledge and just to move this technology forward. This is our collaborators. Yeah. Thank you very much for your attention. Any questions? Yeah.
Yeah, I recall that during the oil spill in Gulf of Mexico, the U.S. used some kind of resources to make small micro droplets of the bacteria that digest how does your approach impact those? I know that you said cannot add. I mean, is there any scientific study to say about the pros and cons of using a solvent or approach versus a solvent approach?
Yes, so basically it's two different perspectives of how you treat the oil. So in our case, we just try to really fast response, and you see that even the longest time is 32 minutes. So the ones you mentioned in the Gulf of Mexico is in the time frame perspective is really long if you're gonna weigh the material. So I think that the advantage in using the solidifiers is actually the rapid response that you can apply. Yeah.
For a spill in open water, you were talking about maritime environments or like the Gulf of Mexico spill. Mm-hmm. How would you actually recover the oil in an open water body? I mean, it's all sinking. It's
not going to sink for a while. It's going to stay on the surface. Depends, of course, of agitation.
On the surface.
Yes, this is designed, like, let's say the oil spill happened. They have to be ready to do this, and they have to have the equipment, because if there's too much agitation with time, remember the microscopic picture of this emulsion, it's gonna sink. But this takes hours, sometimes days, right? So if you're fast enough, you kind of get the notification and you're ready to go and you spray it when it's on the surface. It's just solidified and stays there, it doesn't sink. Let's say the weather permits, right? So you just have to have a boat ready or something. You literally scoop it, and it's not that the layer is really thin. It's 1.2 millimeters. It's gonna spread and it's gonna stop at 1.2 millimeters. So basically, it's really thin layer. It's not that much. So that's why you don't need that much of the solidifier to press it. It's kind of penetrate pretty and solidify it to the, even if it's a layer, it's solidified all.
Okay, and you said it's a powder, right?
It's a very fine powder, yeah.
Can you disperse it with a backpack sprayer, or how do you? What's the
the engineering aspect is up to whatever you want to use, but you want to do a very thin layer on the top. It's like any type of sprayer that is available commercially. In our case, we just shake it. We use a shaker. Yes, and a person who was shaking. But it's the engine. We didn't investigate some engineering solution, but those are pretty common and well known. The good thing with the spraying, because when you're in the middle of the spill, you're okay. But when you get to the edges, then when you start spraying chemicals in the water, and you don't want to do this, but it's really, if you stay kind of the edges, you see the white powder just going and absorbing to the oil, which was pretty cool. Yeah, because it's highly hydrophobic. It just look for the oil and go there. It doesn't stay in the water.
All right, and one last question. When you're saying it's scoopable, can I use something like a cleaner, a scooper you would use for a swimming pool, or it's
yes, and yes. So anything. So basically, when they brought me the last year of the project, they say, okay, we need evidence that is scoopable, and the only thing I can think of is rheometry. Right? So I didn't show those results yet. They're still coming back, but you go and you see that it's 1 Newtonian liquid, you absolutely make it non-Newtonian. So it's not hard, but like it's almost like you can scoop it with anything you want, and then the water will drain. It's very hard. So yeah.
Thank you.
Yeah. Yes.
How long will it remain scoopable?
It's permanent. Because of the changes, those are hydrogen bonding changes. There's really strong bonding. It's basically, to reverse it, you have to treat it chemically or with heat or something. So it's basically, it's permanent change. Sorry?
They sink in the oil.
It will sing if you leave it with waves. And what the wave does, because if the high agitation, they will start infuse small water droplets, which is changing the density. But this is only happen in a long term, so this is designed to act in a short term. Any other questions?
In your biodegradation study, where you see the bacteria in it,
Yes.
very cool.
Yes.
Yeah, I think that's more into it. Do you use seawater or other, because you probably did it in a small vessel.
The results I show for the bacteria are from the pilot plant, actually. From the pilot plant, we sample at different heights. We have different ports, and yeah, sometimes when we don't have time to analyze it right away, they freeze the samples, so it's still ongoing. But yeah, yes, it's almost complete. 1.5 months to go. Yeah. Thank you so much. Any other questions? Thank you very much, guys.
That's great. Yay, I'm very excited about this one.